right, and welcome to the lesson 4.6, Advanced Algebra Notes, the fundamental theorem of algebra. This is big time here. So um, let's do it. It's building off a lot of concepts from the previous lesson. We'll start with exactly that, the fundamental theorem of algebra, and explain what that is and look at how we can use it in some of these situations. So let's jump in right away. For your notebook, what is the fundamental theorem of algebra? There's your heading. This is from the textbook, obviously pretty technical. As far as, I mean, you're welcome to read through it. Basically, here's the gist of what you need to know. When we look at a polynomial, pick any one. Well, we'll do an example here in a second, but any polynomial, when we look at the degree of the polynomial, that tells us the number of zeros that that polynomial has, how many we can expect. Or if we were solving an equation, we can we know exactly how many solutions we should expect to get. Okay, so it does sound, it's a kind of a fancy name, like I joked about, the fundamental theorem of algebra. It's not overly complicated, when you kind of boil it down to it like that. The couple little just caveats, that does include repeated zeros. So, for example, even just real small here, if I asked you, let's just say it was something that was already factored that ended up like this. If I were to unfactor this and kind of multiply it back out or expand it, we'd see this was a third degree polynomial. So we would say, hey, we're expecting 3 solutions. But when I come to like my answer and I say, hey, what are the solutions to this? The only answer we're ever going to write is 3, x equals 3. So you got to be a little bit careful there when you look at it and say, hey, you lied, Mr. Kroll, there's only one solution there. This fundamental theorem of algebra counts basically three times, because, if you were to expand this, you'd have x minus 3, x minus 3, x minus 3. They're technically, if you want to get super technical about it, there would be 3 solutions. They just ended up being repeated. Okay. And this also extends to, any combination of real or imaginary. So we'll see that in this lesson, where we'll start to run into some solutions that end up being imaginary. So most of what we end up doing should feel kind of like we did in the previous lesson, 4.5. Let's do it. Let's look at a few examples here. So the first part is meant to be super simple, and don't overthink it. When a question's asking about the number of solutions or zeros, it's I guess maybe as good of any time to just review what's the difference. What are we talking about? Solutions, zeros? Why do we kind of use them somewhat interchangeably? It's basically, are we talking about an equation, like a mathematical equation where we're set equal to 0? That's something that we would solve and get solutions for, versus more of a generic function. This is like y equals, we don't have a specific output here. When you're talking about more of a generic function, that's when you would use the term zeros. That's the only difference there. In the end, I mean, as long as everything's standard form, which I'm looking at these, they're both in standard form, there's no reason to overthink either one of these. If I asked you how many solutions does this first equation have, I don't even really care I don't care what they are. I see this is a third degree polynomial. There are 3 solutions for that. Don't make it harder than it has to be. For how many zeros does this function have? Again, I'm looking at the highest degree. It's in standard form, so it should be the first power I see, the first exponent I see there, 4. So we would say there are 4, my pen is writing funny, 4 zeros. Okay. Now, I can't tell you, are they imaginary? Are they real? Are they repeated? I can't tell you that just by looking at it like this. We'd have to do a little bit more digging to find that. Okay. So that's kind of the first part. Fairly simple, I hope. Let's look at a couple here. Okay. So let's do, oh my gosh, 5th degree. Find the zeros of the polynomial. So we basically, the one difference that we saw from 4.5 to 4.6, what changes here is 4.5 asked us to find all the real zeros. This is just saying, hey, you know what? I don't care if they're real, imaginary, just find them all. All right, so that's kind of the one thing that changes. Our process actually stays exactly the same. So I guess using our new fundamental theorem of algebra, I can look at this if I want to like preset up a spot for solutions, x equals whatever it's going to equal. But I know for a fact there's going to be five total solutions here, or zeros, I guess, once I set this equal to 0. So yeah, let's jump in. So basically with this high of a degree, our only option to start this is going to be using synthetic division, using that rational root theorem from the previous lesson, saying, let's lay out these coefficients. One, now don't miss, we're missing a second degree right here, right? There's fifth to third, I'm sorry, we're missing a fourth degree right here. So don't forget to account for a 0 there. I'm still using that 1, -2, -12, -8. I'm trying to write small. I have no idea how far we're going to have to take this one. And then, again, possible rational zeros are factors of 8 over factors of 1. So automatically we should be checking 1 and -1. Every single time should be your first two that you check. But then I'm going to look at 2 and -2. I'm never going to check 3 or -3 because those aren't factors of 8. But 4, potentially 4 and -4. Let's not get ahead of ourselves. Let's just start with 1. Okay, so I'm going to start with 1 here. Drop down my first one, and then we roll. 1 times 1 is 1. Add them up. I'm trying to not make any mistakes, but go fast enough to keep the video relatively manageable. 1 times 1 is 1. I write it again. 2. 1 times 2 is 2. 2 plus -2 is 0. Yeah, that's not going to be good for us. So I can already tell at this point this isn't going to work out. What are we looking for again? We're looking for this to be a 0. It's not. Okay, so I know I'm taking 1 off the table. That is not one of my solutions. Start over. It's a little bit, this process, it can potentially be time consuming, but I guess, a problem like this where the numbers are small, it's not, most of that you're doing in your head, I would hope. Let's check -1. That's the next number we should be checking. Drop down the 1. Let's see, 1 times 1 is -1. Add them up. -1 times -1 is +1. Now we're adding there. -1 times 2 is -2. Add them up. This, I think, will change things here a little bit. -1 times -4 is +4. If I add those, I get -8. -1 times -8 is +8. Look at that. That didn't take long for us to hit one there. So absolutely, -1 works. I'm definitely going to have to scroll here on the screen. It's just not going to work out with the space and everything, but it is what it is. So here we go. We're building our answers. That's 1 down. I guess 4 to go, knowing that there's going to be 5 total. If I didn't, I honestly can't remember right now, but if I didn't in the previous lesson mention, I would believe that I would have, but I'm always, I guess I fear missing a repeated 0. Because remember, as we said, there's the potential for any one of these solutions to be repeated. I definitely want to check and make sure that -1 is not repeated. So as I get into this one here, I'm going to repeat on these new numbers now. I'm going to set up another synthetic using 1, -1, 2, -4, and -8. Okay, I wouldn't go back and check 1. Whoops, I need a little bit more space than that. I wouldn't go back and check 1. I already kind of proved that 1 did not work. It wouldn't magically start working again now. But I am going to check -1 again to see if it's a repeated. So I drop down this 1 as always to get going, and then it's the same process. -1 here, add those up. +2 here, 4. We're going to get -4 there. -4 plus -4 is -8. And sure enough, I kind of had an inkling, I'm not going to lie, that that was going to happen. But yeah, so I mean, you might ask, well, what's the big deal? So what? We already had that on our list. We don't get to add another number up here. It's not like I'm going to write -1 again. But what I might do is say, okay, that actually is accounting for 2 solutions right now. 2 of the 5. So, okay, just check it off as double. I don't have to indicate, you don't have to tell me like, hey, this was repeated. The other win by checking that is we're down a degree. We started at 5th degree. When I hit here, we went down. This is a 4th degree, coefficients and constant. We hit again on -1. Now we're down to 3rd degree. It's not a bad idea, and I can already tell by looking at the numbers, if I were just to rewrite this now as one, this one right here, 1x to the third power, negative 2x to the second power, plus, 4x minus 8. Just by looking at that, I can kind of tell, and I'll try to explain where I can see it, and maybe you can see it too, that once I get to third degree, the only option I potentially have it would be to factor it would be by grouping. And I can tell that these numbers are going to work by grouping, because basically with this 1 and this 2, this is 2 is twice as big as 1. I've got the same thing going on here. 8 is twice as big as 4. So I think it's at least worth trying to see if I can factor this by grouping. And that's just me. If you wanted to keep going with synthetic, you could. The hard part here is we need 3 more answers. 3 more zeros here, because we know we got to get to 5, and I don't know if we're going to be able to get them all using synthetic. But you could go and move up, probably check -1 again and make sure it wasn't repeated a third time. But at this point, I'm looking at this and I'm seeing a factor by grouping. So that's how I'm going to finish this one. I'm going to look here and say, you know what, I can group these together. That's a plus, that's a positive 4 there. And look at that first group and say, hey, I can take out just an x squared. It's not a ton. What does that leave me in here? An x minus 2. If I reverse engineer this one, knowing how factoring by grouping works, saying, hey, this has got to end up as x minus 2. The only thing that has to come out of here is a 4. That's already positive. That's already negative. So if I take out a 4, I would say, hey, let's put these two to finish the factoring. Let's put those two together. Whoops. Oh, no. X squared plus, that's a positive 4, so plus 4. And then I remember I just used one of those as x minus 2. And we were still equal to 0 that whole time. Okay, so I think I can get another relatively easy findable solution. What value of x makes this equal to 0? 2 minus 2. So one of my x's are going to have to be 2. So I can scroll up here. This is going to result in x would have to equal 2. Awesome, we'll take it. I climb up and say, all right, I've got another solution, x equals 2. So there's 1, 2, 3 answers accounted for. Where are my other 2 going to come from? You got it right here, x squared plus 4. And I know there should be 2 solutions to this because it's an x squared. Now this one, just be careful. It's not a difference of squares. We've seen a lot of that lately, I feel like, but it's got to be difference. This is sum. So this one does not factor as x plus 2, x minus 2. That's only if this is subtraction. So how do I finish it? Well, I would basically set that expression, x squared plus 4, set it equal to 0, and then use your algebra skills to solve that. Subtract a 4 from both sides to get x squared equals -4. I'm going to square root both sides. And going back to chapter 3, we said it was okay to, we can square root negative numbers. There's nothing wrong with that. What's our process here? It's been a while, so let's review it. I know on the left side I'm going to be down just to an x. Don't forget to set yourself up for a plus minus here on the right. Actually, I'm just going to leave it like that for now, because that's how we initially learned it was. Don't forget the plus minus. In a second step, the plus minus is now there forever. The easy fix on the -4 is just, we're talking about imaginary numbers here now. So the square root of -4 involves bringing an I out front and just saying, all right, let's work with that as if it were a 4. And then I guess in this case, because the 4 is perfect, we can just do the square root of 4. But if I needed to simplify what was underneath the radical, I would do that. Square root of 4 is 2. So we would finish by writing my solution as the positive -2, or positive -2i. I just stuck the 2 in front of the I. So there are my other 2 solutions, positive 2i, -2i. So if I go all the way back up to the top here and say, oh, what are my other 2? Positive, -2i. Check, check, 5 total. We're good. So it's a great look back at a lot of skills we've looked at: synthetic division, factor by grouping, this particular one. solving using square roots, knowing what to do with imaginary numbers. We're going back and kind of leaning on some concepts from chapters ago. So great lesson. Let's look at one here. I know this one's got a little bit of it's something else, a new kind of wrinkle to it. So let's jump in. Let's do it. Find all the zeros. We can do it. That just, remember, involves setting equal to 0. It's 4 terms. I'm looking at this one thinking, oh, thank God, it's only third degree. So once we drop a degree, we'll be at the quadratic at second degree, which is great. I would initially look, can I factor by grouping? And I'd say no. I mean, I know what this first one would be an x minus 7, and I'm just not going to get that to work here with the x minus 7. So always, I guess, check for that stuff. It does make things a little simpler, but we got to go with what we got. So right now, I'm going to start educated guessing and checking using synthetic. So 1, -7, positive 26, and -20. Right, I didn't miss any. They're all there, accounted for. And we're just starting with positive, negative factors of 20 over the factors of 1 there. So here we go. 1 and -1 should always be your first two to start with. Drop down your 1. And then get it rolling. 1 times 1 is 1. Add them up, -6. 1 times -6 is -6. Positive 20. 1 times 20 is 20. Holy cow. Best one ever. If I'm building my answers, I'm already, I'm already set up here. I know x equals 1. That's one of my 3 solutions. Love it. And my thought process is, like I said at the beginning, once we hit on 1, we're already down to quadratic right here. I'm done with synthetic. I have way better options than synthetic division and guessing and checking. I'm jumping right to 1x squared minus 6x, right? That'd be an x, and this would be my constant, positive 20 equals 0. Now, this is the first time we're seeing this here, I think, like this, where most of what we've seen so far is we can factor this. Give me 2 numbers that multiply to 20 that add up to -6. And we're going to be here a while because there is no combination, right? This is not going to factor. So even if you were like, you know what, I kind of want to keep synthetic checking, go ahead, check -1, check 2, check -2, check 4, -4, 5, -5. None of those are going to work because basically if this is unfactorable at this point, you don't have any more integer solutions or zeros. It's all going to be irrational or even potentially imaginary solutions. So it's a great time to review another concept from the past. I would say at this point, what are my other 2 options? If factoring doesn't work, I would say for most people, probably the quadratic formula, what we were a little bit stronger with. Your other option, which I guess I'll do both here to review concepts. I won't do it for all the examples, but it doesn't hurt to look at it here. I would also say complete the square is, in my eyes, a better option. I think it's easier if you know what's going on there. Let's do them both. Let's review them both here just so we have it. And I guess I'll let you decide on kind of where you want to go. So let's start with quadratic formula. We'll do that one. First, the problem with quadratic formula is you got to know what it is, and it's big and clunky and complicated. So here's my quadratic formula. X equals the opposite of b plus or minus big square root of b squared minus 4ac all over 2a. So I got to get all this stuff where it goes, which, okay, it's not the end of the world. Let's get them in there. X equals, let's see, the opposite of b is going to be positive 6 plus or minus big square root b squared, so negative 6 squared is positive 36 minus 4 times a, which is 1, times c, which is 20. All right. And that's all over 2a, 2 times a, which 2 times 1 is 2. Okay. Everything's in the right spot there. Now it's a matter of simplifying a little bit at a time. Don't try to do too much. I would say let's leave the 6 and then the over 2. It's really just a matter of what's my discriminant. Is remember what we called this number, 36 minus 4 times 1 times 20. That's 36 minus 80. I think we're talking 44 there. Actually, I'm sorry, negative 44. Okay, so that's all I did was simplify what was underneath that big square root. From here, all right, if I'm 6 plus or minus 2, I'm going to just kind of separately here review, hopefully relatively quickly. We just saw it a second ago. How do I fix this negative 44? First thing is to get an I out front. Okay, that was easy. Next thing is to break that 44 up into factors of 44. And I want one of them to be a perfect square. So that's where the 4 is coming into play there. 4 times 11 is 44. I'm breaking that 44 up into those two numbers. I do the square root that I can do. So in this case, the square root of 4 is 2. We just saw it a second ago. So 2i times the square root of 11. So that's how I'm just going to kind of box this and say this was like a separate review on putting something in simplest radical form. So that's what this negative 44 becomes basically over here. Can I squeeze it in there? Maybe change color here. 2i times the square root of 11. So the last thing on this one would be we'd want to reduce anything that we could reduce. So remember we said at the time when we learned quadratic formula, it's okay to split it if you're not sure if you can reduce certain parts. Put the 6 over the 2, and then put the 2i square root of 11, but that's also got to go over 2. But maybe it's easier to see that way and see like, hey, you know what? Actually, I can reduce this. 6 over 2 is 3. And then don't worry about the 11. It's really just a matter of would these two numbers be reducible? And they are. They actually cancel out. So I'd end up with I times the square root of 11. Those are my last two solutions, right? Just like before, there's a plus, there's a minus. These are two different answers, 3 plus I root 11, 3 minus I root 11. So like before, if I scroll all the way to the top, we get 3 plus minus I square root 11. Two solutions. Now I'd encourage you to stay with me here. I know you're like, well, I'm done. I'm moving on to the next example. Let's see, can I copy this and bring it all the way down? I just need a little space to work here. Just hear me out. I know it's been a while since we've completed the square, and I know for the first time around, that wasn't everybody's favorite, but maybe it's time. I don't know. Maybe it's time to figure it out here. So remember this is the notes on completing the square, or just a review of it to potentially finish this one. I'm trying to give you some options. I like this one because there's way less simplifying. So the thing you have to know is just kind of how it works, though, obviously. So this was the one where we set it up as we actually want just the A and B terms kind of together, and then the constant term on the other side of the equation. So I had to subtract it from both sides. I subtracted a 20. That's why it's showing up over here negative. And then I set myself up with these blanks, and I put one there and there so I don't forget. If I add something to this side, I got to add it to this side. Okay, what am I going to add to this side? Well, we're looking to create a perfect square trinomial. So the process was basically half of this number, 3 squared. 3 squared is 9. And again, that's not that hard. Those are easy calculations, right? 3 squared is 9. It's just a matter of knowing, like, where did that come from? Why are we doing that? So the whole advantage to doing that basically is now on the right side, it is what it is. I've got a negative 11 over here. Negative 20 plus 9 is negative 11. Looks familiar. I've seen that before. The right side, though, I've made something, that perfect square trinomial, that's going to factor really nicely. And this is just, you got to go back and look. I actually don't even remember the section. 3.3 maybe for complete the square. This is going to, or you just two numbers that multiply to 9 that add up to negative 6. That's negative 3. X minus 3 squared. And maybe you can kind of see how it's going to finish. I mean, so if I can get there, how would I finish this and we should get the exact same answers we got with the quadratic formula. I would square root both sides of the equation. Sweet, over here, that takes care of that, leaving just x minus 3. I square rooted both sides of an equation, so I got to make sure I set myself up as plus minus. But here's where it's nice. I don't have to mess around with that 11. It's 11. There's no 44 or negative 44. So I end up just pulling the I out and hanging on to the 11, which is where we ended up before. And then all I would have to do now is add that 3 to both sides. So plus 3. Just stick it in the front. So x equals 3 plus or minus I times the square root of 11. I don't know. Like, to me, it's way less simplifying. I don't have to worry about reducing a fractions, putting something in simplest radical form, pulling out that perfect squared. The reason this was a good candidate for complete the square is this was an even number, and this was a 1, which we're pretty much seeing almost unanimously where this is a 1. But because this was even, we could go half of it squared and get that number. It'd end up being kind of a nice number. So just something to think about. We got to the same spot, maybe a little less work. Just good review for us. Okay. Either way, we finished up with 3 solutions like we thought. So yeah, we should hopefully be okay with that. I mean, that's our first big use the fundamental theorem of algebra. It's basically just knowing the amount of solutions you get. We kind of just extended 4.5 to account for imaginary numbers. The last part is also an extension, really, of 4.5. We probably could get by calling this lesson. I know in the textbook it's a separate lesson, but I'm trying to drag this down here. This should feel really familiar if you did 4.5 already. So this is the second part of the notes. It does have a fancy name, the complex conjugates theorem, but it works the same way that the irrational roots theorem, irrational conjugates theorem. I can't remember the name of it. Went in the previous lesson. I don't mean to sound dumb there, but basically what we're taking away from this is they come in pairs. And we've seen that already. Complex zeros are always going to come in pairs or conjugates. So if we just saw it a second ago, if 3 plus I square root of 11 is one of your zeros, guess what? 3 minus I times the square root of 11 is also one of your zeros. You can't have one without the other. It works with just kind of, well, it worked with the other one too, right? With example 2, we saw positive 2I, we saw negative 2I, had to be there. We could literally click through the last 2 examples and see you have to have one. You can't have one without the other. Okay, so that's what this is saying. You'll always come in pairs. Yeah, not much more to say there. I don't think so. Just add that to your notes. The last part is the question or the problem should look familiar. We did these. We just did them with square roots before. So it's that same kind of verbiage at the front. It's a lot of technical. The process that we lay out here ends up just kind of, it's always going to work out basically where we end up with, we're going to have a function of least degree. That's just what I show you here is it's going to work out that way. We're going to have real coefficients and we're going to end up with a leading coefficient of 1 just throughout this process. Okay. What makes problem to problem different is that, okay, it all depends on the zeros that we're going to use. So recalling back, how do we write our zeros? Like, these are like our answers basically, right? We're kind of starting at the very end of the problem. We just finished this problem and said, hey, all that work, I just got done. My answers or my zeros or my solutions are -2 and 5i. Well, I've already made a mistake because we just talked about that complex conjugates theorem saying that, hey, if 5i is one of my solutions, you need to know that so is -5i. Okay. So there's stuff built in here. I can see that I've got 1, 2. We came up with the third one. So that means there's 3 total zeros or solutions. This is going to be a third degree polynomial. It better be. What's always right before getting the zeros? Usually it's seeing them as factors. Now in this case, it didn't work out because we didn't have it factored. But how could you write your zeros? It's always x minus whatever your zero is. X minus 2, x minus -2i. So we're going to do that same deal. I guess if you didn't do 4 or 5 and you're looking right now, the next step is after I lay out my zeros is to write them all as factors. So you can start your fact. I know I've got 3 zeros, so I'm going to start with x minus. I'm going to have x minus, and I'm going to have x minus. Just as a rule of thumb, just always start off writing your factors as x minus. Now, as each one of these go in there, I might have to tweak the signs a little bit. X minus -2 really shows up as x plus 2. X minus 5i, okay, that's x minus 5i. And x minus -5i is going to show up as plus 5i. Okay, so that's kind of the next step. Account for all zeros, if any missing ones. Most of the time, the ones I give you are missing one because I want to see if you know that they come in pairs. Second step is write them as factors. And then I guess third is like reverse it. Go from factors. How would you turn this into something? I want my answer to look something like this, where there's just x to the third, x to the second, x, and 20. Probably not 20, but you know what I'm saying? Like, how do we go from this to looking like that? I need to FOIL these. Now, definitely start just like before. Start with the ones that have the i's going on. Just hang on to this x plus 2 till the very end. We'll FOIL that back in afterwards. This is another good review for us. As I go to FOIL, x times x is x squared. X times 5i is positive 5. You can write it different ways, 5ix or x5i. Some people will write it. As I go here now, it's a negative 5i times x. So that's going to be negative 5i x, which hopefully we're seeing right now. These are, because they're conjugates, these should drop out. Okay. And the last one, this is the one that can sometimes be tricky. This is negative 5 times 5, so that's negative 25. And then I times I is I squared, which hopefully we remember that, I squared, that actually has a value of -1. Right, I'll even write that on here. That -1, or I squared has a value of -1. So this is really like negative 25 times -1. So when it's all said and done, when I FOIL these i's, this x minus 5i times x plus 5i, I'm going to get dropout in the middle here because they're opposite signs. I'm going to get x squared, and I actually get just negative 25 times -1, which is positive 25. It's actually kind of cool. Like, it simplifies down to just that. That's really nice. And then just don't forget that, we said we were going to set aside that x plus 2 for now. So, now is the time to bring it back in, x plus 2, and then we'll FOIL it back out one more time. So we go x times x squared, which is x to the third, x times 25, which is 25x, 2 times x squared, which is 2x squared, positive. Last but not least, 2 times 25 is 50. I guess you just have to, in this case, because of how this one worked out, just write it in standard form. And it did tell us to call it f, I believe. So f of x, let me just double check so I don't lie to everybody on video. It said write a polynomial function f. So it just says call it f, and when it's all said and done, f of x equals, get it in standard form, x to the third plus 2x squared plus 25x plus 50. That's it. So, I mean, again, I like that. It's basically this right here could very well be a problem that I say, hey, tell me what the real zero, tell me what not the real, but tell me what the zeros are of this. All right, start. I would actually factor by grouping and go from there. But, right, we're literally reversing everything that we're doing. I mean, minus the synthetic division because we don't have to do that. But we're reversing that process of going from here's the polynomial, tell me the zeros. Now it's here's the zeros, show me the polynomial that these come from. So last one, look at that. Not the worst, could be longer lesson. A little bit of a beast to finish with. So very, very, very similar process. I think just the multiplying your imaginary zeros or your factors gets a little complicated. So stay with me, make sure you finish this one. Same deal. I would probably just start with the very finish. And how does every problem usually finish? 0. So x equals 2, x equals 3 plus I, and we need to know that if 3 plus I is a factor, or is one of the, not a factor, but I'm sorry, one of the zeros, 3 minus I, the conjugate, also has to be one of the zeros. What did we do on the last one? We kind of set it up where it was x minus, I'm going to leave a little space because I know these are bigger, and then x minus. Now this one, like before in 4.5, it can be a little bit more complex. Let's see, if I'm plugging in each one of these zeros, this goes in here as x minus 2. Great, that's fine. Because there's a plus here, I always write it as in like another set of parentheses. So x minus 3 plus I, because technically that's the entire zero. And then same thing over here, x minus 3 minus I. All right, so it's already looking kind of complicated. We're going to do the exact same things before. Like let's hold on to this to the very end. Let's clean up all this I stuff. We know those have to drop out at some point. I just don't know exactly, how it's going to go. I know we're going to need space eventually. I guess we're probably fine for now. So what I do, I don't like these double sets of parentheses. So for a split second, basically, I'm going to distribute this minus here and go minus 3 minus I. And then do the same thing here. Minus 3, now plus I. So x minus 3 plus I. And then because we're there, I'm asking, because we're there, basically, if I'm looking, I've got these first x minus 3's the same. If I group those together, I end up with, I can FOIL this basically. And it looks weird with a FOIL because there's 3 terms. Before I put those in there and get into it, I'm going to show you the way that I always do it. But you could ultimately, as long as you take care and stay organized with everything, just multiply this out. X times x, x times negative 3, x times I. You're going to have 9 different total multiplications. Okay. I don't know if my way is necessarily, I'm not saying it's better or shorter. It's just the way I feel like over time, most people have done better with it. So hear me out here. I would group these first 2 things together, the x minus 3, because they're the same, and say, hey, you know what, those are the same. We can group those and just treat that as like one thing that is part of our FOIL. So I really technically kind of only end up with, I'm going to multiply this thing times this thing. Let me color code it. Maybe that'll make it stand out. So that times that, which, okay, yeah, that's still not great. X minus 3 times x minus 3. I'm going to have to FOIL that. But then here I get, I said I was going to do colors and I didn't. Let's do x minus 3 times I. What is that? That's positive I times x minus 3. And then when I go on this one, I get negative I times x minus 3. So that's negative I times x minus 3. Okay. My last part of the FOIL would be, let's see, let me use purple here. Negative I times I, so that's negative I squared. Do you follow what happened there? We distributed the minus. We lost that inner parenthesis for a split second. And then I said, hey, I recognize that this x minus 3 and x minus 3 were the same thing. And I guess it really doesn't matter that they're the same thing. But I said, let's just treat that as one group. Because then I can maybe shortcut my FOIL a little bit. Instead of having 9 things, I really only am multiplying 4, a true FOIL, first, outer, inner, last. And this doesn't look nice right now, right? Like, holy cow, yeah, that's really helpful, Mr. Kroll. But it's very similar to the last one. Look at these 2 things right here. I've got positive ix minus 3. I've got negative ix minus 3. Gone. If one's positive and one's negative, it's like adding 2 plus negative 2. Or 5i and negative 5i. They're gone. Okay, that just shrunk things significantly. We said this, going back to the last section as well, has a value of negative 1. So this is really like minus, don't forget that minus isn't a part of the I squared. Minus negative 1. So in the end, when it's all said and done, I got to make sure I go plus 1 on whatever happens out of this. Okay, so yes, if you're sitting there yelling at your screen saying, you're going to do another FOIL, you're absolutely right. Like so I end up probably doing the same amount of FOILs maybe 8 versus 9. It's up, whatever. But I think this is an easier FOIL to do. X times x is x squared. X times negative 3 is negative 3x. X times negative 3 is negative 3x. Negative 3 times negative 3 is positive 9. These don't cancel, so this is x squared minus 6x plus 9. Now, just don't forget, this little guy over here is still a part of this. We just kind of crossed all this stuff off. It's still on that same line. So I got to make sure that I go, really the things that need to get combined is this 9 and that 1. So it is a beast. Don't get me wrong. It's going to take practice in doing this. But when it's all said and done, x squared minus 6x plus 10, it looks so innocent, doesn't it? Like, oh, that's just x squared minus 6x plus 10. That's what you get when you FOIL this thing with this thing. So that does take practice. It's going to take time. Now, again, don't forget, and I almost did there, that this x minus 2, that's part of the problem too. I got to make sure I account for that 0. But I would think that if you can get to this spot, what is it? I forgot already, x minus 2. I just need to make sure that I bring that down. But that should be something you learn to do, maybe even in middle school. There is this type of FOIL like this. So FOIL is not the best term, but we got to multiply it out. X times x is x to the third. If you're a box person, where you're going to do it like this, and multiply like that, you're absolutely welcome to. I'm not going to. That's not how I learned it. That's not how I do it. But if that's the situation we're in right now, basically. Let's see, negative 6x squared. We got 10x. Let's change colors here. Let's go negative 2x squared. Let's go positive 12x. And let's go negative 20. We're so close. Get your stuff together. I think we can jump right to it. It said call it f again. So f of x equals, what stuff do I got to get together? This is solo, so x to the third. I've got a couple x squared terms. So that's going to be negative 8x squared. This is usually where I make my mistakes too. I'm feeling the end of my video and oh my gosh, we're so close. Don't screw it up though. 10x, positive 10x, positive 12x, positive 22x. And then last but not least, we've got this negative 20 hanging out there. And again, it kind of looks innocent at the end. If I said, hey, find the solutions of this, I think most people are like, okay, I could synthetic division, factors of 20 and blah, blah, blah. If you only knew what we went through to get there, right? Some of that crazy FOIL stuff and all those i's. So that's where we ended up there. I think we've got a polynomial named f, least degree, real coefficients. You'll never end up with i's in your stuff. It looks just like a normal polynomial. So you got to figure out a way to get those i's to cancel. So play around with it. If this way that I did with the double grouping didn't make sense, try it where you're going to just do the 9 FOIL bit. I don't mean to do it again. I don't need to do it again. But where you do like the 9 and maybe it works out a little better for you. So there's different ways you can kind of approach it there. See me if you want to see it done that way. So I think, unless I'm missing something or forgetting something, I think that kind of puts a pin and wraps up find conjugate pairs and use them to write polynomial functions. Yeah, we're good. We did it. So that's lesson 4.6, fundamental theorem of algebra in the books. I will see you in future lessons.